start recording. All right. So this is for number 2. As for number 3, please give me a, oh, here it is. As for number 3, and we wonder if this function is continuous. Will I upload the tutorials on Canvas? Yes, I will. Probably and hopefully today. Now, f is continuous if and only if the limit when x tends to 0 of f of x is equal to f of 0. Okay? So, we calculate the limits. Limit when x tends to 0 on the left of f of x is the limit when x tends to 0 on the left, square root of minus x sine of x to the power of minus 4. Now, this tends to 0 and this is bounded between minus 1 and 1. So this limit is 0. If we go to the other side, we use the same reasoning. This is bounded between minus 1 and 1, and this tends to 0. So this limit is 0. Both side limits exist. They are both the same. So we can say that the limits exist. The limit is equal to the function. So the function is continuous, which is written like this. That's a calligraphic C. This.
Can I ask something?
Yes, you can.
So we don't need to use squeeze theorem to solve this?
You don't need to use what, sorry?
Squeeze theorem to solve this.
No, not really.
Because I was thinking like we don't even need to know the limit of sign because we have limit of square root of absolute value, square root of absolute value of x. If that is 0, then it doesn't matter what limit of sign is. We can just ignore it because 0 multiplied by whatever it is will also be 0.
The thing here and the main difficulty of this problem is that this sign, this limit is not defined when x tends to 0. So you have to resource to other properties. In this case, we will use that it's bounded.
But does it matter? Because it is the two functions are multiplying with each other. If the square root of x was not there, then it would be the limit would not exist.
Exactly.
But now you're multiplying two functions and one function is like 0, then the other limit should be 0. That's like limit property.
Yeah, limit respects product, right? This is the limit of f times the limit of g. That's the reason why we have to resource to such a tool. I thought this would be way less funny as an exercise, honestly. Anyway, let's move on. Now, this was nice what it lasted. Now we're going to enter what we like to call real mathematical analysis. And not real in the sense that we work with real numbers, but real in the sense that we are already entering the topic. So the first and probably most important concept that you have to know is the derivative. I need to write this here for you. It's written f prime of x, and it's the limit when distance h tends to 0 of this thing over here. So with that in mind, I'm going to start solving exercise 11 from section 2.1. You can find it in page 100. Now, this means evaluate. So what we are going to do is we're going to derivate function x squared, and then we're going to evaluate it. Here I'm going to give you a table with some common derivatives. And so let's see. I mean, what can go wrong if we try to derivate this, right? Derivative of y is the limit when h tends to 0 of x plus h squared minus x squared divided by h. This is the limit when h tends to 0, x squared plus 2xh plus h squared minus x squared divided by h. This thing cancels this thing, and then we have h that multiplies 2x plus h divided by h, right? This cancels out, and this is 2x. More generally speaking, if we are dealing with a function of the form x to the power of n, the derivative is n times x to the power of n minus 1. So each time we do this procedure here, if instead of a 2 we put an n, the term in x to the power of n cancels here, and what we have is that small little beautiful monomial over there. So now we evaluate. The derivative of function y in x0 is 2x0. Questions? Okay. So in a last step, interpreting this result means that at point x0, the tangent line has a slope 2x0, which means parabolas go pretty fast if you think, go up pretty fast if you think about it. Now, another little refresher. This is the axis. This is function f of x. And this is the tangent line. Is it? No, whatever. This is better. Now we're moving into section 2.2, page 107. And I'm going to go through number 11 again. Which is now. How do we solve this? Well, first we are going to apply the definition. Derivative is the limit when h tends to 0. This thing over here. And then I will show you something cooler in order to solve this. This is the limit when h tends to 0, x squared plus 2xh plus h squared minus 3x minus 3h minus x squared and plus 3x. So what cancels here? X squared cancels with x squared, 3x cancels with 3x. And this limit is the limit of 2xh plus h squared minus 3h divided by h. I read your question, Mahmoud. I will answer at the end of this lecture. First, let's finish this limit. Now, we see h multiplying, h multiplying, h multiplying, and h multiplying, so we can take common factor. This cancels here, here, and here. And this is 2x minus 3. Now, the exercise asks us to express this using differentials. The differential notation is the following. Instead of y prime, we say this. We say the derivative of y with respect to x. How y changes when we change x. This would be the complete exercise. Now, questions about this? Good. Okay. Now let's take it one little step further and solve exercise 43, which you can find in page 108. We know y is t to the power of 1/4, and we are asked okay, what does this mean? This means evaluate the derivative of y respect to t in the point t equals 1/4. Okay, mathematical notation is, it looks like it's there to scare you, but it's actually there to save you work. Because we could have been asked to evaluate the derivative of y with respect to t in the point t equal 1/4, but we can also write this. Okay? When you see one of these functions and this bar on the right side always means evaluate. So we're going to do exactly that. We know that, and sorry, if we know this, we have this function, we know that its derivative is n t n minus 1. Okay, we have seen it here. So this doesn't only apply for entire numbers. So we're going to actually use it. So our y prime, or our derivative of y with respect to t, is, by following the formula, and if you want to see it in fraction form, because it happens, this is 1/4t in power 3 of any of those work. Okay, now we evaluate. And so we're going to put it here. And why am I choosing this formula? Because this is 1/4 in power 1. So what we have here is actually 1/4 in power 1/4, which is kind of beautiful if you ask me. This is 1/square root of 2. Now, questions about cryptic mathematical notation and evaluating. Okay, then moving on. We have already seen some basic examples of how derivatives work. Now we're going to talk about the rules of derivation. Now, 2.3.1. Now, I have to tell you about the first rule of derivation, and that is linearity. Okay? Derivation is what's called a linear operator, and that means that if we give it to functions, then it respects the sum, and it respects multiplication by scalars. Okay? In the course in vector algebra, somebody may have mentioned that differentiation is linear. This is what it means, and this is what we're going to use here. Y prime is 6x minus 5. Let's see. We use our formula for monomials. This is 3 times 2x minus. Okay, this is 6x minus 5. Good. No mysteries here. Derivative monomials is basically like counting. Now, we're moving to something a bit more funny. Okay, the amount of mystery this problem has is absolute zero. The only problem is that we are dealing with a lot of parameters, and it looks scary. It looks what's the word again? Yeah, I think scary, impressive. I don't know. The idea is that it looks way more complicated than it should, but we're going to remember another rule of derivation. We have the product of two functions, and we derivate it. We get f of x times g plus f times g prime. Okay? And if we have a quotient of functions, the derivative sorry, forgot the x. Divided by this. There might be a minus sign here, so let me check something. Okay, that's correct. You know the best thing of having a whiteboard? You can reserve a corner for calculations. Now, we're going to use that rule, the quotient rule for derivatives, in order to solve that, okay? Firstly, if we derivate, here we have the derivative of this is A, the derivative of this is C, and so the derivative of f of our function is derivative of the first times the second minus the first derivative of the second divided by the second squared. Now, let's see what this offers. This is ACX plus AD minus AXC minus BC divided by this little monster over here. This cancels with this because A and C are numbers. And we have AD minus BC over CX plus D squared. Now, you may want to expand this, but express like this monomial square is way more interesting from a saving space perspective. Like, it's way more obvious what this is written in this way than if you go this. It's longer, it's bulkier, it doesn't see, it's not very seeable, I would say. It's pretty horrible if you ask me. So we're going to leave it like CX plus D squared. There we go. Now, questions about number 25. No questions about number 25. Okay, then 10 minutes break. We will start again at 11:05. Elementary functions are polynomials, trigonometrics, exponentials, logarithms, and yeah, these are basically the elementary functions. All you have to know about them is that they are differentiable in all its domain. They actually belong to a class they belong to class C infinity, which is infinite times differentiable functions. This is very important. This is a concept that you will find pretty often. There is the most important ones are C0, C1, C2, and C infinity. Class C0 is of the continuous functions. Class of C1 is of differentiable functions. Class C2 is of twice differentiable functions that you can derivate and then derivate again. And C infinity is the class where all functions should belong if the universe was nice and fair. Unfortunately, it's not, but we still can do some stuff. So yeah, let's move on. Okay. We're moving on with number 29. Okay, these functions tend to look very complicated, but in the end, once they are broken into small pieces, they're pretty manageable, and that's what we are going to see in this one. We have y is x squared plus 4 times square root of x plus 1 times 5x power 2/3 minus 2. So I'm going to call this F1, F2, F3. Because there is some preliminaries that I have to do here. We have F1 prime is 2x. F2 prime is this thing over here. F3 prime is this little monster. Now, since we want to calculate the derivative of F1, F2, F3, what we are going to do is we're going to gather it as a product of 2. So our first little monster we're working with is F1 times F2, and then we multiply by F3. So by the rule of product, by the chain rule of product, the derivative of this would be so we have to calculate F1 times F2 prime this is F1 times F2 prime plus F1 prime times F2 this is 2x square root of x plus 1 plus this. So now we can start replacing things in our main equation. And what we have here is times x3 plus F1, F2 times F3 prime. So our derivative looks something like this. Now I'm going to write this in the first row, so we can work with it in the next one. Now is where the magic should happen. We look here. We want to shrink this a little bit, and we observe here that x square root of x is x in power 3/3, and x squared times x in power minus 1/2 is x in power 3/2. So we can put these two terms together. And now we have to take care of the other two terms. This is 2x, and this is 4 times 1/2, so 2x minus 1/2. Like this. And this one, I think we can leave it the way it is. Okay, so now we have no other choice than to multiply this little monster here. So we start, first one, 25 over 2, this is x, plus, sorry, this is not x. This is way better. This is a 10. Minus minus 4x and minus 4x power minus 1/2. Okay, I will agree with you that this looks pretty ugly. Well, it does. It really looks pretty ugly. And still, it's kind of what they have. So let's play with it a little more. Now I have to expand this again. This is x in power 5 over 2 plus x squared plus 4 square root of x and plus 4. Implicitly, I'm trying to tell you here that you have to be very good at operating with fractions to derive polynomials properly. And so let's see what we can take from here. Doesn't look like much. But I'm going to call all these P1, and so we have P1 plus this is good, plus of x in power 5/3 plus R6 plus and now let's compare if we can figure something good out of this. Now we compare terms with the same exponent. We start with the biggest, which is 13/6. Okay, vale. So this is 95/6 x in power 13/6. So we have taken care of this term and this term. Now we move with the x in power 5/3, and we have 40/3 of x in power 5/3. This term and this term. We move with x in power 1/6. Now we have these monomials that look a bit weird, but we have minus for x, we have minus for minus 10 and plus 40/3 of x minus 1/3. Okay, so this is one way to do it, but it looks ugly. Anybody here who doesn't agree, this looks incredibly ugly? Exactly, you got it there. So if a solution looks this ugly, as they generally do, but we have to learn to simplify problems. The way to avoid this, as the product of three monomials looked good in the first glance, in the end it hasn't turned out as well. So we have to start admitting the big possibility that a human error in calculations has happened. So since this is being recorded, I'm going to do a completely different approach and compare the results. So instead of multiplying the derivatives, what I'm going to do is multiply all this, turn it into a big string polynomial, and see what happens. I multiply this, we have x in power 5/2 plus x squared plus 4 square root of x plus 4, multiplying 5x 2/3 minus 2 and this is equal to plus wait. Plus 20x in power 2/3. And now with multiply with minus 2. Minus 2x in power 5/2 minus 2x squared minus 8 square root of x and minus 8. You know, the good thing about exams is that it always looks like you're not going to have time to review your calculations, but you always do. Mark these words, you always do. Actually, the time spent reviewing an exercise is at some point can be more valuable than the exercise itself. Now, if we derivate this, we're going to follow this derivation rule for our monomials, and we have 5 times 19/6 with x in power of this minus 1, which is 13/6, plus 5 times 8/3 times x on power this minus 1, plus 4 times this x on power 1/6, plus 20 times 2/3 in power minus 1/3, minus 2 times 5/2 x in power 3/2, minus 2 times 2x minus 8 1/2 x minus 1/2, and the 8 vanishes because it's 0. Now, we're going to put together the terms with the same degree on x. They seem to be all different, which is good. So here we have 95/6 x in power 13/6 plus 40/3 of x in power 5/3 plus this thing over here plus 40/3 of x minus 1/3 minus 5x in power 3/2 minus 4x minus 4x minus 1/2. Okay, this still looks pretty ugly, but it's good. Sometimes the solution to a problem is just like this, and you have to work around that. Now, these that I have showed you are the two main approaches for solving derivatives that involve products of functions. Which one you want to use? It's already up to you. I suggest that you have a good grasp over both because you may need them. Otherwise, we can move on to the next one. Okay. Now we know the following. And we want to calculate the derivative with respect to x of x squared divided by f of x when x equals 2. So I want you to tell me why this is equal to 2. And if it's equal to 2. And then we'll solve it. Oh, okay. So let's solve it then. The derivative of this function by using the formula for the quotients of functions, that's 2x f of x minus x squared f prime of x divided by f of x squared. Okay, now we have enough tools to calculate all this. We replace x with 2, and we have 4 times 2 minus 4 times 3 divided by 2 squared, which is 4. So 1, 2, 3, and this is minus 1. So no, it was not 2, and nobody told me. This is the reason why I study math. Now, I'm going to move on to the next section, 2.5, and we have exercise number 23. Now with this exercise, I want to illustrate you to the most important rule of differentiation, and that's the chain rule. The chain rule says that we have a composed function like this. The derivative is f prime evaluated in g of x times g prime of x. Doesn't show. There we go. Okay, now this is the single most important rule of derivation. If you know this to heart and you know how to apply it, then most of the exercises that will open to your eyes will be suddenly half as hard. So what exercises 22 to 33 want you to find, roughly they are in page 121. Is to express this. So we're going to do so. We're going to use the chain rule. And the chain rule says that f prime in 5x minus x squared is equal to the derivative of all this is f prime evaluated in this point times the derivative of this. And this is 5 minus 2x. Now, how do we translate this to something we can understand and work with? For example, if we have the sine function, and we would go here, if we want to derivate the sine of 5x minus x squared, before my pen dies, if possible, then by the chain rule, our derivative will be f prime evaluated here. I mean, the cosine of all that is here inside times the derivative of what is inside here, which is 5 minus 2x. This is the chain rule, gentlemen. Now, I'm going to do one more, and then we can call this a day. Okay. Going to the number 25. Number 25 is the same exercise, but we have square root. Of 3 plus 2f of x. Okay. So, first of all, we notice that this is 3 plus 2f of x in power 1/2. So what are we going to use? The chain rule. And what we have here, okay, it's still visible. Is chain rule. Derive the function with the argument that is inside. Now, the function here is the square root. So our derivative would be 1/2 of all that is here inside in power minus 1/2 times the derivative of what is inside. The derivative of 3 is 0. The derivative of f of x is s prime of f prime of x. So this will be 2f prime of x. We cancel this out, and we have f prime of x times. We can put it in a more visual way. And here it is. Now, the chain rule is simple in structure, but it requires a lot of practice to take over. So I recommend you do exercises 22 to 30 to pick up some handling to, put this a little bit into practice, because it looks pretty spectacular. It honestly is pretty spectacular if you ask me. But this is a little bit complicated in concept. So I need you to practice a lot with the chain rule. And I mean a lot. I mean literally as much as you can. We still haven't seen derivatives of trigonometrics, right? No, that's for Thursday. Okay, that's good. Because once we get into trigonometrics, things get a little bit more funny. So yeah, I think we're gonna have a good time, guys. Now, 15 minutes for final questions. Can we discuss a little bit about implicit differentiation? I think it's soon for that. we will do it, but no, I don't think it's proper to do it today. We'll probably cover it at the end of Thursday's tutorial, if the case goes. If I remember correctly, you sent me number 27 from section 1.3. Please confirm if that's the case. Okay. Okay. I'm going to use linearity here. Okay, so this is the limit that x tends to infinity of x square root x plus 1 minus now. Now that I have separated this limit into two limits, it is very clear that this limit is 0. First thing of all, this limit, it's a polynomial in the infinity. In the numerator, we have something that has degree 3 halves, and down we have degree 2, which is greater. So the denominator rules, and the denominator says this limit is 0. Now let's play with the other part. Okay, I got to put the minus sign inside. Do you see it now? Let's do one more step. I'll leave you this as a small spoiler. What did I do here? I took 2x, I multiplied and divided everything by the square root of 2x squared, which is a square root of 2 times x. So it comes out as the square root of 2 of x squared because it's multiplying by x. And here we have a square root. In infinity, this is 1. And we have a monomial in x squared and a polynomial in x squared on the other side. So the limit is the quotient of the coefficients in the highest grade. And that is, ladies and gentlemen, minus 1 over 2 square root of 2. Just to frighten you a little bit to finish the day, this is the kind of problem that I will give you in an exam.
Could you please repeat the final step one more time?
Yes, I can actually write it in 2 steps for a better reading. It's minus x now this comes out. It comes out as a square root of 2 times x. The square comes from the x that is already out multiplied. When we jump into infinity, this square root is 1 because this is 1. This is divided by infinity, so it's 0. This is divided by infinity, so it's 0. So our limit depends on this term, that is on x squared, and on the highest term denominator, which has x squared. And there you go. Beautiful, huh? This was a good one. Thank you guys for showing up. With this, I think we're going to give this tutorial number 3 as finished. So keep practicing, keep studying. Don't go out into the call without a code. Although you will see me doing that every single day of my life, that's kind of my choice and I have to live with it. but you have the choice to put on a coat and be warm and comfy in the outside. So please do it. Don't forget to drink water. Doesn't matter at which time you're watching this, it's always important. And yeah, thank you for joining. This is it. Take a look into the derivatives of trigonometrics, because they are very simple and they will help us a lot in the upcoming tutorials. Thank you.
But so I have a
See you on
question.
Thursday. Yep. Yes, Marco?
Well, I can't find them. They're not uploaded on Canvas. Do you hear me?
Now I do.
Okay. I think about the tutorial. The tutorials what I didn't upload it on Canvas. They aren't uploaded on Canvas.
I will upload them. I will
Okay.
upload them shortly.
Okay. Thank you.
All right. Thank you, guys. See you on Thursday.
Thank you.